Guess who's back? Gravitation constant. This is all about calculating how big of a force of gravity there is between two objects. Get ready, Lego. The universal gravitation constant is noted by capital G. A man named Henry Cavendish was a guy who considered it. It's a beautiful, large number that links everything together. Notice the crazy units. Newtons involved, meters and kilograms. When all's said and done, though, this is going to be bundled up in a beautiful little package where you can figure out exactly how much force of gravity there is between two objects. Let's use that capital G, which is different than little g, which is the acceleration of gravity, but they are quite related. But let's take that and move it to the next level. As Newton was talking about, that all objects experience gravity, when we include the gravitational constant and multiply it by both masses and divide it by the distance squared, we end up getting the total force of gravity. So this is the equation that we are going to use. A couple things. Note to self. When you up either mass, what happens? For example, say you doubled mass 2. That would double your force of gravity. Say you tripled mass 1. That would triple your force of gravity. Say that you increase your distance by 2 times, or double it, right? So you'd have it over here. But 2 squared actually gives you 4, so you'd be dividing it by 4. Oh, the inverse square law. So all the things we were talking about earlier hold true with this equation. Don't forget that the big G is the universal gravitation constant. Write down that. You'll need that. You won't have to memorize it, but it's good to know. And remember, all those beautiful units are going to cancel out in just a bit. If we did a problem where we wanted to figure out the force between two regular-sized people, so an 80-kilogram person and a 60-kilogram person, and if they're about 1 meter apart, could we calculate that? You bet your rear end we could. If we're looking for the force of gravity here, we know that the big G is 6.7 times 10 to the negative 11th. If we take the small mass and the larger mass and divide it by the distance squared, when we do all the math, we end up with an incredibly small number of 3.2 times 10 to the negative 7th. Now that incredibly small number is nothing compared to, say, the boy's weight, where if we took his F equals ma, or F equals mass times acceleration of gravity, we took his mass times acceleration of gravity, we just rounded up to 10 here instead of 9.8, you end up getting 800 newtons. What does this mean? Why do we even care? It means that even though the boy and girl are attracted to each other, they're nothing compared to the attraction they have towards the ground, towards the earth. So they aren't being pulled towards each other. They're standing right there, just gazing into each other's eyes, wondering if either one of them liked the same TV shows, maybe the same type of food, or even chocolate. Now, how do we figure out gravitational acceleration? Well, if you remember, the force of gravity, which is the same as weight, is equal to mass times the acceleration of gravity. Well, if we plug that in for our big gravitational equation, we could put the mass and the acceleration of gravity there. And lo and behold, look what happens. The mass of your body cancels out. And what you're left with is just the acceleration of gravity is equal to the constant times the mass of Earth divided by the distance squared. What does that have to do with anything? Look at the next slide and it'll explain everything. It means that gravitational acceleration only has to do with the mass of the Earth and how far away you are from the center of the Earth. Which means the further away from the center of the Earth you are, so the bigger this number gets, the smaller the acceleration of gravity gets. What does that mean? It means that actually we've been kind of lying to you. The acceleration of gravity isn't 9.8 meters per second squared always on Earth. In fact, the higher up you go, the less it is. Let's take a look at the chart to see exactly what I mean. So here's the definition and the proof that I lied to you. On the Earth's surface, yeah, the acceleration is about 9.8 meters per second squared. But you go about 1,000 kilometers above the surface, that acceleration drops to 7.33 meters per second squared. Keep going up, the acceleration of gravity goes down. It falls with a smaller change in velocity per second. So sorry we lied to you, but for most part, 1,000 kilometers above the surface is way up there. So even if you're on a mountaintop, you still are pretty darn close to that original 9.8 meters per second squared. So don't cry or throw a hissy fit. Last sample problem. Jimmy is attracted to Betty. Good luck, Jimmy. Jimmy's 90 kilograms, which we can put in for mass 1. Betty's 57 kilograms, which we can plug in for mass 2. And they're standing about 10 meters apart from each other, which we can plug in for distance. When you end up plugging in the gravity constant, thanks Cavendish, both masses, and divide by the distance, don't forget to square it, you end up getting a number that's pretty sad. It's 10 to the negative 9th. 1, 2, 3, 4, 5, 6, 7, 8. Boom. It's that in newtons. Kind of a sad number, isn't it? Once again, it's a good thing. Otherwise, Jimmy and Betty would get stuck together, and eventually, if they got tired of each other, they would have no choice but to remain together. Good job, Jimmy. Good luck, Betty. Have a great day, everybody. Thanks for listening to the talk about gravity and the constant. Let's start solving some problems. Let's start understanding the world a little better. Peace out.